Good. So it's a great pleasure to be here to share our recent progresses, and I'm gonna talk about molecular ions, which is composed by a single ion and Rydberg atom. And we're gonna show a little bit about the theoretical aspect of these molecules, and also a prospect for detecting such a molecules in our hybrid atom ion setup. Okay, here we go. Probably I have to click once for. Oh, yeah, good. Thank you. So this is the team from Ulm, and Marcus Dice and I and Johannes Hecker-Denschlag, and also Dominic Dora involved in this project, and three of us are joining this conference. Good. So actually, we call ourselves as a Barbie group, Barbie project. And so this Barbie actually stands for a barium rubidium ion experiment. So basically what we do is that we trap barium ions using the pore trap. And this is a picture of the pore trap in our vacuum chamber, which is pretty conventional one. And we laser cool it so that we can cool them down to the millikelvin temperature, so they organize a linear chain of ion. And yeah, so this is a schematic of our system, and which has two pairs of radio frequency electrodes, these blue ones, and also one pair of the end cap, so that we can confine them tightly. But we also trap atoms, and for trapping atoms, we use cross dipole trap configuration, and these two red beams are the dipole trap, and then we make an overlap between ions and atom to have a direct contact between them. And our main interest is to test the chemical reaction between ions and atom, especially at the low temperature. But recently we found out our system is more capable for other applications, such as molecular spectroscopy and also a state-to-state chemistry for the neutral atoms and so on. So I'm gonna quickly introduce our ongoing project later. Yeah. So this is the the list of our project which is running in our Barbie setup, and the first one is the atom ion chemistry, and then in this project we have been able to see the charge exchange collision between barium and rubidium atom, and also we recently saw molecular formation by this three-body process, basically the atom ion process, and we confirmed that we can create the molecular ion in a specific situation, and this is a molecule which Olivier mentioned in his talk, and we got a little insight about the dynamics of these molecules. Basically, what we measured is that the how quickly such a molecule, weakly bound molecules, are dissociated by the laser light, and also how quickly these molecules decay in the ladder of the vibrational state in our ground state potential. So unfortunately, I'm going to talk about different kinds of molecules, which is in a highly excited state. But today we have a poster. Actually, Marcus Dice is going to present the detail of this work, so you can come to us to discuss this later. And the second one, as we call state-to-state chemistry with neutral atom. And actually, we use a quite high-density atom cloud of rubidium, and it is well known that in such a high-density situation, we have a three-body processes, three-body recombination. Yeah. And so in a three-body recombination, we all know that this ends up with a production of dimer and also the atom. But the thing is, the energy released in such a three-body process is quite high, so that and it's way higher than higher than our conservative optical dipole trap depth, so that the molecules in atom actually pops out very quickly from our trap. So in that sense, such a molecules is kind of elusive molecules. But we somehow developed the idea of a nice ionization scheme, so that now we can ionize these molecules and keep it in our pore trap. And and even we can count the number of these molecules because it's kept forever in our trap. And on top of that, we found out that our MP scheme is actually capable for dissolving the quantum state of the molecules, such as vibration and rotation. And we are exploiting this feature to study the precise um, chemistry in a state dissolved fashion. And actually, Paul Julien is going to talk about the detail of this state-to-state chemistry later on this conference. And the third one is the one which we're discussing in this talk, and we call it charged-Rydberg molecules project. The essence of these molecules is that if we have an ion, an atom nearby, actually the long-range interaction between ions and atom can bind them together. Basically, they can form a molecules, and especially for the atom, which is in the excited Rydberg state, we could find a nice bound state as we see here. And this is what I'm going to show in the next 10 minutes. Okay. So, let's go. Okay. So let me quickly explain how it works. So all of us know that the interaction between ions and atoms are well modeled by a charged dipole type interaction. And this, here's an ion, and this ion produces the inhomogeneous electric field, and this field actually polarizes the atom next to him, and this induced dipole again interacts with the electric field. So it's natural that if this atom is in the excited state, such as Rydberg state, the interaction strength is kind of boosted up because of this large polarizability. And indeed, the group from Amsterdam actually demonstrated this effect. And what they did in their experiment is that they pumped their atom into the Rydberg state, and they measured a few orders of magnitude higher reaction rate compared to the ground state system. So this actually implies that for the atom ion chemistry, it's quite useful to use Rydberg state to control the interaction strengths. And what we did in this work is that, so we actually checked the pair interaction of the ion and Rydberg state specifically for the p state, and we found out, so as we see in this corner, so this is a picture of the potential excited state for the 7p state. We found a little pocket here, this one, and this one is actually the molecules which I am talking about, and we are looking for such a molecules in our experiment as well. And this red lines are the predicted position of the molecular bound state. Okay, good. Yeah, so this is the typical energy landscape of ion and Rydberg atom system. This is nothing but a stack map, but the electric field is provided by a single ion trapped here. And so we have atom ion distance in the x-axis, and y is the energy. So our state is now this p state. And if you look at this p state, this is go all the way down from here to there, and it's distorted because of the stack shift. And then and this stack shift is induced by the field from the ion. And the thing is, so this manifold line with so-called hydrogenic manifold is actually crossing with one of the p state, and our interest is here. This is orange zone because this p state and one of the high L states are crossing and making a avoided type crossing. And actually this state supports a bound state in a highly excited state like here. And we want to create our molecules by pumping from this S to the p state by laser. Okay, so let's take a closer look of our molecular state. So this is an even closer look of our state, which is coming from that dashed box. And so we found out that the bond ranks here we define the bottom of this harmonic potential is now like 100 nanometer, and if you increase your principal quantum number to up to 50, actually it goes like a few micrometer. So this means this is a quite long range molecules. And if you plot the scaling of these bond ranks and also the vibrational spacing, it looks like that. And in the left panel, we have how we have a figure which shows how the bond ranks evolves as a function of the principal quantum number and also the spacing of the vibrational state. And what we learned from this analysis is that actually the spacing of these vibrational states are in the range of the hundreds of megahertz or tens of megahertz. And this is good news because the laser which we use in our experiment is actually much narrower than such a energy scale. So we have a chance. This tells us that we have a chance to resolve the state in our measurement. And we found that in parallel to our work, there's a little bit of similar analysis from the group of Michigan, and this also gives a similar feature. So that's our motivation to create these molecules in our experiment, in our project. Okay, so this is how we want to create these molecules in the actual setup. So we start from a single ion trapped in our Paul trap, and we bring a cloud of rubidium atom, and we dip this ion into the core part of the rubidium atom cloud, and we shine the laser, which have wavelengths of about 300 nanometer, so ultraviolet range. And this laser excite the ions and atom. Both of them are in a scattering state to create the molecules in the excited state. So this is nothing but photoassociation. And once we create the molecules in the excited state, they are quickly dissociated, and then this is ionized, and these ions are kept in our Paul trap, and we let the new atom cloud bring into the system and let them collide to count the number of atoms and also the number of the ion, because the number of the ion is depending on the number of the ion we have in our Paul trap, because for detecting the number of the ion, we exploit the atom-ion elastic collisions. And now such a measurement is in progress, and we hope that we can bring update somewhere later. Okay, so this is my conclusion. So we talked a little bit about the theoretical aspect of the molecules we are planning to detect in our system, and we found some properties of basic properties of our Rydberg molecules. And actually, we already started our measurement, and here's the preliminary data. But what we found is that there is a little bit of technical challenges. Basically, the effect from the Paul trap is doing some work. And let me explain. So here we have the schematic of our Paul trap, and we have to apply high voltage to trap ions. But the finite size effect of our dipole of our atom sample actually is detrimental, because even though the system is very compensated, a small small field from the Paul trap is creating an additional noise ion. So we did have a quite visible, quite clear structure of the spectrum, but all of them are turned out to be coming from the ion trap itself, the field from the ion trap. So we have to overcome this problem by having a new idea to suppress this effect dramatically. So the measurement is going on, and let's see. Let's hope we can do this later. But the great news is that the molecules which we talked about is quite recently demonstrated by the group of the Stuttgart. So what we predicted is not wrong, at least. And yes, I'm running up my time. So thank you very much for your attention.
Thank you. Thank you very much for this exciting talk. Now, Sadiq will speak first.
Right. Very nice. I have a question and a comment.
Okay.
So the comment is that we tried such experiments with rubidium 2 plus
Okay.
in 2015, 16, I don't know.
Mhm.
And we see extremely strong dissociation
Okay.
due to the cooling fields.
Oh, cooling field. Okay.
Yeah, due to the cooling fields for rubidium. And my suspicion is that that class of dissociation channel will also affect your experiment.
Okay.
So just look into it. This is some
Mhm.
PRL from 16 or 17.
Okay.
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 Uh,
Noted.
there's another. The comment is. So the question is, what is the effect of the pulling of the compensated ion that you have? Okay, due to the Rydberg atom
Mhm.
and subsequent excitations of motional excitations of the ion atom system,
Okay.
basically, on your experiment going to be.
Okay.
We have also studied this, and the excitations are quite massive, actually.
Okay. Okay. So when you say cooling field, does it mean the laser for cooling the?
Yeah.
Okay. So, thank you.
Yes, now Stefan, yes, please.
Oh, so yeah, so okay, so I think you asked the effect of the pulling effect of the, yeah, okay, so we assume that so actually the molecules we are looking for is way distant from the iron core, so it's micrometer away from the iron. So indeed we have such a curve which actually pull out the atom to the iron, but we assume that if atom comes at the right distance, the laser actually pump this two collision partner to the excited state very quickly, and then dissociate it very quickly, then ionize. I hope I could answer you. Yeah.
So thank you for the interesting presentation. I have two questions, if
Okay.
I may. So the first one is, I understand, okay, the experiments are still in progress, right? But what sort of lifetimes do you expect for these molecules?
Very good point. So we actually did not precisely calculate the lifetime of the molecules, but for the atomic lifetime for the B state is in the range of a few microseconds. So we have to do it. Yeah. So for the atom, but for the molecules, we expect this is more. This should be shorter, and
Yeah.
Yeah. Yes. Exactly. So. Yes.
Exactly. Yeah.
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 So okay.
Yeah.
So there are two things I have to mention. One is that so we did calculated the potential for the molecules, but we never actually elaborated did an elaborated analysis for how much leakage we have for this little pocket. Yeah.
Do you have an estimate or?
No, I didn't name it.
No. Okay.
And the another point is that so generally speaking, this molecule is very fragile in terms of the sensitivity to the electric field. So even a tiny bit of E field can dissociate the molecules. So it's like a quite sensitive sensor for the electric field. So we know that we could create the molecules, but this is supposed to be ripped off quite in a quite short time.
And how are you planning to deal with the problem of the fields of the ion trap, which
so yeah,
I understand wasn't
yeah.
the problem in the Stuttgart
To be honest,
experiments,
we are pretty struggling, and in my opinion, so as I said, so our atom size is 50 micrometer, but I think I have to compress it more, like, so basically we have to have a microtrap, like a micrometer scale. And we hope we can neglect the field effect from the outer side. And yeah, so we need some time, I guess.
Okay, so last very quick question.
Thank you, Shinsuke.
Yeah.
So very quick question.
Yeah.
The size of the molecules is about 100 nanometers or so, if I understand correctly.
Yeah,
by the
and
figures.
yeah.
So, if I look at ground state atom ion molecules, our star is of that length, and I was expecting, because of the huge polarizability,
Okay.
to see much larger molecules. So why don't we see? I mean, the polarizability is way larger, right?
For the exciticity, yeah. So what was your?
So I mean, I would expect to see a molecule which is much larger, maybe a micron or so.
Yeah, so this goes. So I think let's see. So indeed, I said the bond length is 100 nanometer, but this is the case for 70p state. But if you go higher, like n equals to up to 50, the bond length shoots up like a few micron. It can be yeah. It's a large molecule.
Okay, so thank you. I think that the next questions we will bring to the coffee break. I think that the following chairing person probably be a bit more strict than I was, but so once more, thanks for all the speakers once more, and now we will have half an hour coffee break. So
Thank
we will
you.
start